the distance between the two plates, right? So one of the most practical way to do it usually is by changing what? Changing the overlapping area. And just basically how it works, right? This is how you change the capacitor's capacitance, right? Here you can see different packaging. You have seen this before. Whenever you open any electronic device or anything, you have seen this type of packaging here that you see, right? So this is generally how they are presented. Also, you can have surface mount capacitor, which is smaller than that, right? and depending the packaging you see here is depending how the capacitor is done. Um, they can have two parallel plates. They can have some type of metal oxides between them. So there is different ways to make a capacitor depending on how which is going to be used, right? So if you have the one on the top, right, all that's usually are electrolytic capacitor, which is basically two plates divided by some type of dielectric material or insulation. Could be paper impregnated with some type of chemical, could be some type of, could be glass, could be just air, or could be some type of plastic, depending on what it is. Then you have the one on the B, which is basically polyester film. And then you have the part on C, those yellow ones there, they're usually with tantalum oxide, which is basically a little, I will show you a picture some point in here. So they're just different type. You don't really have to, it's good to know, but unless you go into electronic components design or manufacturing, then you will specialize most into the component itself, how these capacitors are made and what it make, why they're made this way, right? So this is how I will explain to you how they are done, right? You have, for example, the part A. This is just two pieces of paper, and they are rolled up together to save space. Because if you send this like a, imagine this like a roll of paper, right? A roll like those bounties type of paper towel, right? You roll it up, but if you extend it, it's going to be very long. So that very long, may be very hard to keep constant distance between them. It may be flimsy and may occupy a lot of space. So you can roll it up, and then you have some type of insulation between them to divide the two, to don't allow the material to touch. If you see here, this is here is like a some type of material. It could be aluminum foil. Then you have a insulator in the middle, and then you have the other uh, metallic plate, and then you have these two layers of insulation also. So when it's rolled up, they don't touch each other or touch itself. And you can have here also another type, which is a stack up of uh, also foils, and then you have mica here, some type of plasticky material in between the two, and you have also the tantalum oxide, which is in the middle, isolate those two uh, conductors. That's just the way they're made, right? Usually those ones use it because they can go to high capacitance in very small sizes. This type here, they could be a little bit unstable too. Sometimes they get damaged easily and they explode if they are no, well manufactured. Things like that. These are the surface mount that you have seen before, right? Um, this is your different way to connect to the circuit. This is surface mount. You have to solder these to some conductive lines into the PCB board, the printed circuit board. Here you just have the two leads that also can go into the printed circuit board. This can you be kind of plugged in into something that will look like you can plug it in like an outlet, or you can solder those terminals, Or this one you can just screw it in, and then just like light bulb, like you're screwing a light bulb type of similar connection here, and then they just connect on the terminals. They could be bigger ones, usually used for motors, and they may be also in oil, submerged in oil for cooling and insulation, right? So this is just different packaging, different ways when they can name. They may have a code like this, and you have to read the capacitance they have based on the code, or they can just tell you directly this is a 1 microfarad, for example, plus minus 10%. That means that they can range uh, 1 microfarad 10% up or 10% down, basically. Right, and I show you the voltage that they operate to, right? Sometimes they know the polarity if uh, they are polarized capacitors. You can also have this ceramic type of capacitor. This is very common, um, which is basically the two plates and the two some type of ceramic material as a dielectric in the middle to isolate the two uh, plates, which also depend will affect the capacitance, and this is how the epsilon is calculated from, right? So this is just a surface mount capacitor. It can be very small. If you see here, this is a dime, and this is the comparison of how they could be. Usually using very small devices, and this is all type of packaging. So, oh, this is the oil field one. I'll tell you usually used for cup. If you go into the refrigerator, probably you're gonna have something like this, or any from pump motor, your washing machine may use a capacitor in the motor as a starter. Your fans may have one also. If usually they have those small induction motors, they're going to have a capacitor in there, right? And those are the variable capacitors, right? Usually this one is hard to see anymore. These old TVs used to have this one, and then how this one works is that you rotate this shaft here, and if you see in here, those are like kind of plates that are overlapping here. And then when you move this plate come out, and then rotate like that too. And then when they come out, like this little part here, if you see this little part, will stick out like this and won't be overlapping anymore as much with the other plate. So that's why you change the overlapping area of it when you rotate this. Usually used for all TVs or radios, right? I don't know if you have ever seen that. I don't know. This is old TVs, analog TV are not even used anymore. If you're at a museum, you can see one of your great grandma basement or something, maybe one of those that you can in a TV usually change the it's an inductor, variable inductor, a step, variable step inductor, and you can tune the TV. Usually this one you can use for a radio, and you tune the radio by moving this capacitor, which change your filter, and we'll see later on what a filter is in by the end of the semester. Okay, this is kind of the introduction to the how a capacitor is made, how they look, and things like that. Now let's talking about how to analyze a capacitor now, right? So we kind of have a notion how it's made. We can identify one maybe if we see some of them. Now let's do the analysis. This is the part that we care about here, right? Or we care the most, right? So basically, a capacitor have transient stages because a capacitor is a device that hold on electrical charge as a form of a electric field. So these things doesn't happen instantaneously. They're charging, right? So it takes some time to charge. Whatever the time it is, it takes some time. Short, long, it all depends on the configuration of the circuit. But it takes some time. So it takes some time to charge, then it hold on the charge, and then takes some time to discharge. And then go again and charge depending how the circuit is changing, basically how you close or open that switch. So for example, you see the switch here, and let's say the switch is open as it is shown here, and then you close the switch. But initially this capacitor was fully discharged. So when you close that switch, there will be some current flowing through the capacitor that will charge up the capacitor. Once the capacitor is fully charged, cannot hold any charge anymore. So you will see that that current will start flowing, and the capacitor will go to a steady state until something else change. Then if you start discharging the capacitor, for instance, you open the switch and then you pull, let's say, another switch here, and then you close the switch this way, right? Once you close a switch, now that capacitor will start discharging through that resist, so the current is going to start flowing in the opposite direction. It's going to go here, and the capacitor is going to start discharging again until it fully discharged, and then it goes into a steady state of discharge again. This is why we call that the capacitor have transient stages. And we're going to start analyzing this stage by stage. Basically, we're going to divide this into three different stages, which is the charging phase, when it's fully charged or the switch is open or whatever happened, nothing is changing anymore, and then the discharging phase. That's it. All right? Now, as I told you before, let's do a time diagram. Let's show you here a time diagram here, as we see here. We have the time that's happening, whatever the time it is, and we have the voltage across the capacitor, meaning the voltage across here. The voltage across this capacitor here. And let's divide the time in different ways so we can speak the same language, and you know what stage I'm referring to depending on the timing, right? So for example, let's imagine this capacitor here was fully discharged and we close a switch. Once we close a switch, this is when we start studying what's going to happen. So we make that time equal to 0, right? Once you close a switch, we make time equal 0, and after that, then time start happening for us, start passing, right? And then we study what happened into that time. So when we call, there will be three stages here. We usually will call time minus 0. Doesn't mean that time is negative, right? It meaning whatever time was prior to crossing the switch. That meaning what? The initial state of the capacitor. If we say something like at time minus 0, the capacitor is fully discharged. That meaning is that the initial state of the capacitor just prior to close the switch was fully discharged. That's what it's meaning, time minus 0. And then when we say at time equals 0, that's the point that we close the switch. And then at time positive is whatever happened after, right? So if we see here, this will describe the voltage across the capacitor. So if right now the circuit is open and I measure the voltage here, and as we show in this diagram is 0, that meaning that the capacitor is discharged, the voltage is 0. Then we close a switch. When we close a switch, once we close a switch, it's closed here, current start flowing through, capacitor start charging. And you see here, the voltage start exponentially increasing, right? Start exponentially increasing. So when that happens, there is a voltage start building up across the capacitor. And if you see here, this what describe the function of this curve here. You remember? This exponential function, by the way. Y will be equal to what? Will be equal to 1 minus, if you remember, e to the x. In this case, x is time, right? This is time, the x, right? So this is the equation that describes this function. So if you see here, the voltage across the capacitor increasing rapidly, but then that increase started slowing down as the capacitor get closer to being fully charged. When this capacitor will be fully charged, once it reaches the value of the voltage that's being applied to, right? If this is 12 volt, maximum this capacitor will charge off to 12 volts. After it reaches 12 volts, remember that will be 12 volt here, 12 volt here of the same potential. So there will not be any more potential difference between this point and this point, correct? So if this is 12 positive and this is 12 positive, there is no potential difference between here. If there is no potential difference, there is no flow of current anymore. So when this capacitor is fully charged, there won't be any more flow of current. That current goes to zero. Capacitor fully charged, that's it. You just stay there, steady state, fully charged, and the current is zero. There is no current flowing anymore because this voltage is equal to the voltage here. There is no potential difference across the resistor anymore. The potential difference across the resistor is zero because it is 12 minus 12 is zero. Right? In order to have a flow of current, you have to have a differential potential and you have to have a path for the current. There is a path for the current, but there is no differential of potential. So if you see here now, this is the voltage increasing, right? And then this is the current, right? So when you close a switch, that current jumps to the maximum. And then as the voltage starts building up, that means the potential difference across R start decreasing. The potential difference start decreasing. That voltage that current start decreasing also, right? So the voltage across the capacitor increase, the current start decreasing exponentially also. Until you will see this on your lab also. When you reach 5 times tau, and tau is just a constant that we will know what it is later on a little bit. 5 times tau, we say the capacitor is fully charged. So when you reach 5 times tau, no more flow of electrons anymore. Capacitor is fully charged, and that's it. You just stay like that. But actually, we reach 9.9, 0.99 or 99% of the voltage. So still not fully charged, but we say it's close enough. We call it charge, right? It's like tau 5.1 something tau actually, but 5 is close enough. You see here, you see the percentage based on experimentation. When you reach 5 times tau, you have 99.3% of the voltage of E being applied. So actually 5.01 something something, then you're gonna have almost 100%, right? It mechanically almost never reach 100%, but it stay going up there until we just see it's close enough, is fully charged. right? The same thing for the current. The current jump up and start decreasing here, right? So based on this, we're going to develop some equations, okay? So let's go to the charging phase. The capacitor, right? This is when the capacitor is fully charged, right? Fully charged. The capacitor acts as a open circuit because it just doesn't allow the flow of electrons anymore, because remember, there is no potential difference between this point and that point. If this is 12 volts, that will be 12 volts here, so there is no potential difference here, right? So there will be no more flow of current. This is fully charged. It's at the circuit was open circuit. But now, when the capacitor is fully discharged and we close the current is zero, right? The voltage is zero across the capacitor. What is the voltage across a short circuit? Zero, right? So when we close the circuit, that current will be maximum. Then the voltage starts building up here. Once it starts building up, this starts decreasing until it reaches zero. So you have two extreme states. When the capacitor is fully discharged, at time equals zero, the capacitor behaves as a short circuit. Current max. Current is start flowing. And then when this fully charged is discharged. Based on that concept, you start building all your equations that you will build for the capacitor in order to analyze it, right? So let me just draw some things here, right? I will explain, we're going to do some example. I'm just going to go through the concept of how it is. So let's go down. We understand, conceptualize what is charging phase. Let's worry about the charging phase. And then we're going to develop the equation of each phase based on the knowledge that we have now, right? We're going to build on it. So if we have, let's now think about the circuit. The same circuit as before. The only time we have here is a different circuit. The different switch. That switch can be placed into point 1 or point 2. Now, the analysis that we did for charging is, as the switch was placed into point 1, let's say the capacitor is fully charged now, and then as it's fully charged, that switch is moved to point number 2. So now it is charged through here, this charging phase, right? And as you see, you're going to have, if you keep switching up this from point 1 to point 2, point 1 to point 2, you can build this type of waveform. So you can go from a DC, total DC steady state fixed value to a value that will follow this shape here, right? And that will be the current which describes the voltage across the resistor here, right? For example, this is fully charging, the current is flowing in this direction. Then when it's fully charged, the switch is placed into position 2. Then the current change direction, start discharging through the resistor. Then into position 1, position 2, and then continue doing like this, right? So let's see. We're going to do an example in a little bit. So let's just explain the concept on here, right? So let's develop all these little equations. How I go here? Blackboard, blank. Okay. So let's say we have this capacitor here, right? Let's do a small circuit here. Let's do a small circuit here. And let's call the charging phase, right? So let's say that we have this little circuit here, which will go a voltage source, right? E, right? Then we have a switch. Then that switch, let's say, can be go from position 1, position 2, and then okay. So this is going to be, this is a capacitor, right? This is R, this is the capacitor, right? Which are gonna have a voltage VOC. This is position 1, position 2 of the switch, right? Now let's say at time equals 0, the switch is moved to position number 1, right? It will be just moved to position number 1, right? So when the capacitor moves to position number 1, what is going to happen? This at position 1, right? The switch at position 1, right? Capacitor will start charging, right? And they say this is going to be here. Position 1 is closed here. And you're going to have a current that will flow through here, called IC, right? IC. And this current, what is going to happen? Will start what? Increasing, right? I mean, the current is going to start from the max, which will be IC, right? So now, when the current across the capacitor, what will be equal to? Can somebody tell me? IC in this case. IC, by applying Ohm's law. Remember, the switch is in position number 1. Right at that moment, the voltage across the capacitor is 0. So what is the voltage across R in this case? Just by looking at the circuit, the switch is in position number 1. VOC is equal to 0. At that moment, at time equals 0, VOC is equal to 0, right? So by applying Kirchhoff voltage law, what is the voltage across the resistor right now? Equal to what? Equal to E. The same voltage at the source right now, right? Over what? Over R. But what happened to that? It will stay like that current? No. It will start decreasing as a function of what? Of an exponential, E, that we saw before in the graph, right? As exponential E, which is minus X, right? But it's going to be minus T time, whatever the time will be, over tau. Tau is a Greek letter. Tau, right? And tau is a time, it's called the RC constant. Tau, right? Is an RC constant, which is R times Z. The capacitor, the capacitance times the resistance. That's going to be tau, determine tau. And this is our charging phase, charging, right? This is charging. That is the current IZ, right? So you're going to have this equation. This is the current IC at charging phase, right? Now, let's keep what happened now to the voltage. across the capacitor, VC. What is the voltage, maximum voltage that that capacitor will reach? So when this capacitor is fully charged, right? What will be the voltage across it? And I mentioned in the previous slides, but I'm asking the question. Equal to E, right? But that will be the final stage. Remember, we are not there yet. So you remember the equation of that waveform that we, or that curve that we say is equal to? This is equal to y equal to 1 minus e to the x. So that voltage E, this is E here, will be scaled with respect to time described by this function. So that will be equal to 1 minus e to what? To the minus t over tau. Over tau. And that will be the voltage across the capacitor in charging phase. Any questions so far? Okay. Okay, now what VR is going to be this equal to? The voltage across VR. So the voltage across VR now, this is IC and VC. So what VR is going to be? Can somebody tell me? It's easy. Just Ohm's law. VR is going to be equal to what? To IC, right? Times what? Times R. So what IC is equal to? Well, IC is equal to E. If we look at the first equation here, over R times E to the minus T over tau. All that times R. Okay. So R over R is equal to 1. So VR is going to be equal to E times E to the minus T over tau. And that will be the way to calculate VR in charging phase. Does that make sense so far? Easy, right? It's easy. It's just doing Ohm's law and stuff like that, right? No big deal. What else do we need? We don't need anything else. We have 3 components, right? We have a voltage, we have a resistor, and we have a capacitor. We already know how to calculate the current, we calculate the voltage, and we calculate VR. That's it. So these 3 equations are the important equations on the charging phase. Now, this capacitor, once it reaches charge, right, it's fully charged now. When it's fully charged, it's still at position 1, right? Now fully charged. VOC is equal to E and IZ is equal to 0. That's it. It's fully charged. That's the only thing you need. All right? Do you understand those 2 portions here? Technically, that capacitor now, the switch is moved to position in the air, none 2, none 3, none 1, none 2 position. Ideal capacitor will stay charge forever, but it's not because there is a little leakage current in a practical capacitor. So it's as, this is just for you to know, right? In a practical way, it's as you have a resistor here, and there will be a small leakage current going through here, which will discharge the capacitor with time. That's why if you charge a capacitor and you leave it disconnected, at some point will just full discharge. But let's just make this easier and make it ideal capacitor. But we don't care about, we don't live in this forever, right? So now we need to go to this charge phase. So we did charge phase. Now we keep it charged there. Now let's move the switch after charge. So after we do time -0, switch is moved to position 1. Then sometime happen, it's fully charged. And then sometime after it's fully charged, doesn't matter, it could be any time after. Right? The switch is moved to position 2. Now we will study the discharging phase.